So today we're starting a new chapter. And I'm going to begin with the long exact sequence of homotopy groups that's associated with vibration that I began to indicate last time. So let me begin by explaining a technical thing called the covering homotopy property. Which is a property that's enjoyed by fiber bundles and more generally by vibrations. So suppose that we're given the following data. This is just very general. So supposing we have a map from E to B. At this point, not even yet a fiber bundle. And supposing we have another map Y into B, which I'll call F bar. Now, we say that F bar has a lift. F bar has a lift if there exists a map F that fills in this diagram like this so that the diagram commutes. Now, sometimes this so-called lifting problem doesn't have a solution. For example, if E over B is a principal fiber bundle with a group G, and it's non-trivial, and Y is the same as B, and F bar is the identity map, then a lift would be a cross-section of the bundle. And we know that a cross-section of a non-trivial bundle does not exist. So sometimes some maps do not lift. Okay, so that should make you appreciate that the following is a non-trivial statement. This is the covering homotopy property proper. Suppose that F bar does have a lift. So I'm giving that to you. Okay? Suppose that F bar does have a lift, and suppose that big F bar is a homotopy of little f bar. Okay? That is to say, we have a continuous family of maps, f bar, from 0, 1 times y into b, so that f bar at time 0 and little y is f bar at y. In other words, a continuous deformation of this map, little f bar. Then we say, then the projection P, or the map P from E to B, has the covering homotopy property. Let me just abbreviate that to covering CHP. If there exists a lift F of F bar. In other words, we have E goes over P, and we're saying that then there's a lift. So what I'm saying is if my at initial time t equals 0, F bar has a lift, call it little f. So if F bar at t equals 0 has a lift, F, call it 0, then F bar sub t, the deformation at time t, has a lift F sub t. Okay, so that's a definition. That says that's the definition of the covering homotopy property. And so now we have a definition a fibration is a map with the covering homotopy property. That's the definition of a fibration. And the theorem, which I'm not going to quote, I'm not going to prove, we've got plenty of other things to do, and you can look it up in the math books and the references and the notes, is that a fiber bundle is a fibration. In other words, a fiber bundle has the covering homotopy property. But let us indeed do an example so you have some feeling for it. So let's take a very simple example. Let's take E to be the real line, and let's let B be S1, which I'll identify as the unit complex numbers. Okay, and my map P will take, P takes S and projects it down to E to the 2 pi I S. Okay. So let's take any space Y we like, and let's take F bar of Y to be the constant. So it takes F bar, we'll take any Y just to the identity in the unit circle. Okay. Now this map obviously has a lift. It has a lot of lifts. You could lift it to any integer. Let's just choose the lift, which is F, which takes every Y up to 0 in R. And now let's consider a homotopy of this map, F bar sub t, which I could take it to be of Y, is e to the 2 pi I t. Again, constant as a function of Y. But moving as a function of time. Okay, so what's the lift? So what's ft of Y? Anybody want to say? Is it clear what I'm doing?
Goes from 0 to 1.
Right, so the lift is t. Okay? So, now notice something though. Notice something a little funny. We're going to talk about this a lot more. So, as time evolves, this image point moves, starts at 1 and moves around the circle. And now if I think about what is the image up here, it starts at 0 and it moves up to 1. So it's not a closed path upstairs. We're going to talk about that much more. That's the phenomenon of monodromy. Now, more generally, if I had f bar of y is equal to e to the 2 pi I theta of y for some well-defined function theta of y. I don't allow jumps by 2 pi, but just for some well-defined function theta of y, that's the meaning. That means that f bar has a lift, namely f of y equals this theta of y. So if I can unambiguously take a logarithm of this complex number and call it theta of y and get a continuous function on my space y, that's the meaning of having a lift in this case. Okay? Now, the covering homotopy property says that, okay, if we deform this set of complex numbers to some f bar sub t of y, if we continuously deform that function, then there exists unambiguous functions theta sub t of y that express this mapping, where this is a well-defined continuous family of functions into R. Okay? So it says that if you had no trouble taking the logarithm of this function at time 0, and you smoothly deform the function into the circle, then you're not going to have any trouble with the logarithm for that whole family of functions. Is that clear? Okay, so that's the covering homotopy property.
And this CHP, that's a property of E, V, P, and for given
It's a property of
Y.
it's a property of this map E into B.
For any
It's-
Y.
Yes, for any y. If there exists such a lift, f of f bar, for any y. And for any function, f bar with a lift, etc. It's a property of the projection from E to B. Okay. So supposing we have a fibration. So now let's talk about this long exact sequence. So we have a fibration. So let's, supposing we have an inclusion into E and a projection to B. Okay. And now I'm going to need to choose some base points. So our picture is like this. Okay, so we'll choose some base point F naught here, which goes to some fiber E sub B naught over B naught here. And let's say it goes to some base point E naught here. Okay, so iota is this particular inclusion. Now, recall that pi sub k of x, x naught is the set of homotopy classes of the k-dimensional cube, where the entire boundary of the cube maps to a single point x naught. And recall that maps between spaces induce push-forward maps between homotopy groups. So because we have this map here and this map here, we automatically have maps of homotopy groups, iota lower star, to the homotopy group of the total space, and p lower star to the homotopy group of the base space. Okay, so the first statement I want to make is that this sequence is exact, right? Which, remember, that means these are groups, and it means that the kernel of this homomorphism is the image of that homomorphism. So let's see why that's true. Okay. So first of all, consider P composed with I. Okay, so this takes all of F to B naught, right? So I takes this entire fiber F here into the fiber, this space F here, into the fiber here over B naught, and then the projection squishes it all up into a single point. Okay, so clearly that's going to kill any interesting homotopy. So that means that the image of iota lower star is in the kernel of P lower star. That's the scrunch operation, right? It just squishes it all down to a point, so there's no, so if I take any interesting homotopy class in here, it gets just scrunched down to a point, and that's 0. And that being 0 means that the image of this is in the kernel of this. But now the non-trivial statement is going the other way. Suppose that some F is in the kernel of P star. Okay. We'd like to see that it's, in fact, then in the in the image of iota star. Okay. So let's represent our homotopy class by some f. So this f is in ik of E naught. So it's an ik boundary ik minus 1 into E naught. And let's let f bar be, by definition, p composed with f. So now that's going from ik boundary ik minus 1 into b and b naught. Okay, and they fit into this diagram that I explained before. Now I'm including pairs, but it's the same idea. B and B naught. P goes into E and E naught. And you see, I'm given, by construction in this case, a lift, because I started with F. But now comes the interesting statement. This F bar, you see P lower star of this homotopy class F is the homotopy class of F bar. But we're being given that that's equal to 0. Right? I'm telling you that this F here is in the kernel of P lower star, which is the statement that this F bar is homotopically trivial. But that means, therefore, F bar can be homotopy to a constant. Okay, that is to say, there exists a continuous family, F bar of t, with F bar of 0 equals F bar, and F bar of 1 equals the constant now, taking everything to be naught. But now, because we have a fibration, by the covering homotopy property, there's a lift, F sub t, which takes ik dik into E naught. But that means that F1 lifts F1 bar, which is the map which takes t into B naught. So F1 is in the fiber. E sub B naught. So that means that F1 defines an element of pi k of F naught. You see, it says that we're mapping all of the I cube into the fiber, but we can identify this fiber with this space E, and so therefore it really came from something in the homotopy, K homotopy of F. So that proves the statement. That proves the statement that this sequence is exact at that step. Is there any question about that?
Is this F1 unique of the homotopy package?
Yes. In the covering homotopy property, you can show that the lifting is unique. The lifting is unique for discrete covers. In general, it's not unique. Sorry about that. But it doesn't matter. We're only taking the homotopy class of this. So then you'll have to check that if you make different choices of covering homotopy, you'll get the same homotopy class here. So I'm certainly skipping a lot of details like that.
So that's unique of the homotopy in pi k.
That's correct. That is correct. Yeah.
For my definition of vibration, where does that come from? We define it with E and B with the homotopy.
So Which F? Big F or little f?
The big F. Where is that space?
So wait a second. Again, I answered Ken incorrectly. Excuse me. There can be a kernel in this map.
Oh, right. Yeah.
It's not unique. Excuse me. All I'm saying, that was just wrong. I was thinking too much about discrete covering spaces, which we're coming to, but in general, it's not unique. There can be a kernel in this map, and I don't care. I don't care. All I showed is that it is in the image. That's all I wanted to show. Now, your question. You had an F. So we're asking about big F and little f.
The big F. What is
Yeah.
big F?
Oh, Jesus. There's a big F fiber and a big F homotopy.
Well, I mean the fiber.
The fiber. Okay. We are taking as given that we have a fibration. Okay, and F is just the standard fiber. It's the fiber over some point.
So by definition, the fiber after composing the.
Yeah, take the definition F to B, if you like, E sub B naught. Okay? I like to think in these fiber bundles that there's some kind of standard space which is can be included into many different possible fibers. But I'm just giving myself a fibration, and I'm in the midst now of proving a general property about fibrations. Okay? So the first thing we've proven is that if we have a fibration, okay, then we have this exact sequence for any k. Okay? So if we have a fibration, then we have these spaces, F, E the total space, B the base space, and I claim that we have this exact sequence of homotopy groups. Now, the reason we can really get mileage out of this is because of the next construction, which is something called the connecting homomorphism. So that's a homomorphism, pi k of BV naught, del I'll denote it, to pi k minus 1 of f naught. And moreover, I claim that that connecting homomorphism allows us to have a long exact sequence. So this is, I'm dropping base points here just to save writing, but they should be in there. But now we have this connecting homomorphism. K plus 1, K E goes to pi K B goes to E pi K minus 1, F, etc. All the way down to pi naught. Down to pi naught of B. All the way up to infinity. Okay. So now the key thing to understand here is just the definition of this connecting homomorphism. And once you understand the definition of the connecting homomorphism, you'll see pretty clearly that we have exactness at these other two stages. So let's just describe the definition. Okay, so we give ourselves an F bar in pi k of BV naught. And now the idea is this. Let me draw the k-dimensional cube. So this is IK. But let's view the k-dimensional cube as a continuous time evolution of k minus 1 dimensional cubes. So we have ik minus 1 here, ik minus 1 here, and this is one copy of the interval I. So we're going to be thinking about time evolution as we go up the cube. All right? And so let's give coordinates on this cube, t and s, where little t is the time going from 0 to 1, and s is a coordinate on the ik minus 1 cube. So this F bar here can be thought of as a series of maps, time evolving maps, from the k minus 1 cube into dv naught. Okay? It's just a way of looking at the representative of the kth homotopy class. Namely, f bar of t of s is f bar of t s. Completely tautological. Now, of course, these being part of the boundary, we know that f bar sub 0 of s is the constant map b naught, and f bar sub 1 of s is again the constant map b naught. Okay. So far, so good. Now, we also know that f bar at time 0 has a lifting. After all, it's just the constant map. What could be easier to lift than the constant map? Okay. So let's choose a lift. F bar sub 0 of s, mistake in the notes. It should write f sub 0, not f bar sub 0. That's a very confusing misprint. Choose a lift. F sub 0 equals E naught of F0 bar of S B naught. That's easy. On the other hand, we have this homotopy F bar. So, by the covering homotopy property, there exists a lift F sub t of F bar sub t. Okay, so now consider F sub 1, F at time 1. What do we know about it? Well, the projection of F of 1 is F bar of 1 is equal to the constant map. Right? We agreed that up here, all of this space is going to be naught. Therefore, F sub 1 maps the ik minus 1 at time 1 to the fiber over B naught. But that's just what I want, right? So we take the boundary of this F bar to be equal to the homotopy class of this F1. You see, this is a map from ik minus 1 into the fiber over B naught. So therefore, it defines a homotopy class of k minus 1 dimensional cube into the fiber over B naught, which is just what I wanted. Now, you have to check that there's some choices here that don't matter. And I'm going to leave that to the homework. And I think I'm also going to leave the homework the exactness, which is not too hard. The main thing is understanding this map. In fact, let me give another picture for this map, since it's important to understand. So, as you know, another way of thinking about homotopy is that we have some base point somewhere on the k-sphere, and we're mapping that into our space B to B naught. So we have our base point here, and it's mapping into some kind of balloon sitting inside B. All right? And then over this space, we have our fibration, E, which looks like this. So over, this is E sub B naught. Here's E naught. And now, what are we going to do? So what we do is we consider a loop of k minus 1 spheres. So if you like, put k equals 2. It's very intuitive, okay? You have a 2 sphere. And now I have a loop of circles. Okay? And my circles expand, expand, expand. And then they start to get smaller again as they come around the other side of the sphere. And they come down, down, down. Okay? So I'm lassoing the sphere, the two-dimensional sphere. Okay? So I have a family, as t goes from 0 to 1, of circles which are lassoing the sphere. This is exactly the family here. I'm just explicitly collapsing the boundary of the cube. Okay. Now, for each of these circles, you see, I can lift, so these circles look like this. By the covering homotopy property, I can lift them into circles. So I have circles, circles, circles. But when the lasso comes on the other side of the sphere and contracts to a point again, my circle lives entirely in the fiber. And so I get an element of pi 1. So in this way, I start with an element in pi 2 of the base, and I end up, the last circle is in pi 1 of the fiber. So this lassoing picture, I think, is a very nice picture to have.
Sorry, where's the circle at the final stage? You shrink the circle again.
I shrunk the circle here, but it could be big here. You see, that's exactly the point. The circle's getting tiny here. But because, so I'm starting with small circles, they get bigger, they get bigger, they get bigger, they start to shrink again.
Oh, but that's only on the base.
But that's just on the base. And it could be a big circle up here. At the end, it's shrunk down to a point. But that just means that it's some circle inside the fiber. So let's try and understand something simple. Right. So suppose, for example, that I give you something in the image of P star. And then I make this operation. Well, you see, if I give you something in P star, then I start with a map from IK into the total space. And by definition, this top face here is mapping to a point. So you see that my image under delta is just a point map. And so it's obviously in the kernel. I'll let you do the other direction. So you can prove exactness just using those kinds of pictures. Okay, so let's do 2 examples. Very simple examples. Let's first return to our extremely simple fibration given by the exponential map as E is R projecting down to D equals S1 is R mod Z. So what does the homotopy sequence tell us? Well, it tells us that we have pi 2 of the fiber. What's the fiber in this case? The fiber is Z. Right. So we have pi 2 of Z goes to pi 2 of the total space, which is R, goes to pi 2 of the base space, which is S1. And then we have the connecting homomorphism to pi 1 of Z goes to pi 1 of R, goes to pi 1 of S1, goes to pi naught of Z, goes to pi naught of R, goes goes to pi naught of S1, and of course this comes from pi 3 and so on. All right, now, what are the homotopy groups of Z? Well, pi naught of Z is Z, pi 1 of Z is 0, pi 2 of Z is 0, 0, all the way up. What are the homotopy groups of R? R is contractible. So the homotopy groups are 0, 0, 0, all the way up. Now this sequence is exact. Okay? So what do we learn? We learn that pi sub k of S1 is delta k1 times Z, which fills in a gap I had earlier in the course. And it's actually a lot of fun to see that if we take the generator of pi 1 of S1, so say this f bar of t equals e to the 2 pi I t, and now we apply the operation we just did before, well, I showed you what it was. It took 0 to 1, and so it was 1, which is the generator of Z. Should I show you that again? Remember? So if you map I sub 1, okay, you map the interval according to what we did over there. We have the interval times the 0 cube. We start, say, by mapping to 1. We view this as a homotopy of the constant map. So we lift it up into R. So this t here goes to e, this theta here goes to e to the 2 pi I theta. And then at the end, we end up at theta equals 1. We start with theta equals 0, we end up at theta equals 1. And so we get 1 in Z, which is generating the group Z. Let me give you another example. So we'll prove later that pi 1 of SUN is 0. In other words, we're going to prove that SUN is simply connected. So now our homotopy sequence, so now consider the group PSUN, which I've talked about before, which is SUN mod its center. Zn. Well, then our homotopy sequence tells us that this goes to pi 1 of SUN mod Zn, goes to pi naught of Zn, goes to 0 because SUN is connected, and this is equal to 0, and this is an exact sequence, so these are isomorphic. Okay? And so now we learn that pi 1 of SUN mod Zn is isomorphic to Zn. Okay? In fact, let's give a generator. So an example of a non-trivial loop in SUN mod Zn is the following. Consider G of phi, which is equal to the diagonal matrix of e to the I phi over n, e to the I phi over n minus 1 times, until I get to the end, and I want this thing to be unit determinant, and so I have this. Okay, so I have this matrix, e to the I phi over n, e to the I phi over n, dot, 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 e to the minus I phi n minus 1 over n. Okay, and I'm going to identify my loop as phi is phi plus 2 pi. And the square brackets here mean the projection from SUN down to SUN mod Zn, whose fiber is Zn. Now you see, when phi is equal to 2 pi, this is not the identity matrix. When phi equals 0, it's the identity matrix. Okay, so that's the identity of the group. When phi is equal to 2 pi, this is not the identity element of SUN. However, look at it. You see, if I put phi equals 2 pi here, this is the identity element of SUN mod ZN. Because at phi equals, if I evaluate this, at phi equals 2 pi, I get e to the 2 pi I over n times the identity matrix. Do you see that? Well, that means that in this quotient group, it's a closed loop. I claim this is a topologically non-trivial closed loop. Because what happens if I try and lift that loop into the simply connected covering SUN? My lifting is going to be this matrix. This is also an SUN matrix. But now you see it doesn't close, because at phi equals 2 pi, if I consider it as an SUN matrix, it's not a closed loop in SUN. Its endpoint is this guy here. Is that clear? And indeed, if you go through the definition, the boundary map of the homotopy class of this loop is equal to the generator of Zn. Okay. Let me make just two formal remarks and then give a very amusing example of the use of this exact sequence. Yeah.
So last time you said that pi 0 is not a group.
Right, but I also said that pi 0 of a group is a group.
But if it, in general, I mean,
Yeah, that's a very good question. So, right, so at the end we have what? We have pi 1 of b of b naught goes to pi naught of f naught goes to pi naught of e naught goes to pi naught of b naught. Now you're raising the point, and it's a good point. This we know is a group. In general, these are not groups. If E, F, and B are groups, then they are groups. And then this is an exact sequence of groups. What we understand by, this is still true if we understand this to be exactness of sets. So it simply says that the inverse image of one set is the image of the other. Okay? So, yeah, so there is an interpretation of these last three terms when we don't have groups for F, E, and B. Okay, two formal remarks. First remark. So last time I talked about two ways of classifying bundles over the sphere. Principal G bundles over the N sphere. Okay? On the one hand, let's assume that G is connected for simplicity. On the one hand, I told you that they're classified by pi n minus 1 of G. Remember the construction. We divide our N sphere into upper and lower hemispheres. We have a clutching function on the equator, and that's a map into G, and that defines a homotopy class. On the other hand, I said that there was this wonderful universal space, EG, with a classifying space BG, and we just needed to look at homotopy classes of Sn into BG. Now you could have asked me last time, you could have said, what do these have to do with each other? Why are these related? You agree? This is a question you could have asked. Okay, so now, why are these related? Well, let me remind you that EG has this incredible property that it's both contractible and it has a free G action. So we have this vibration. So let's apply the exact sequence to that. So what do we get? So we get pi k of EG goes to pi k of BG, projecting down. Connecting homomorphism goes to pi k minus 1 of G. Whoops. Connecting homomorphism goes to pi k minus 1 of G, goes to pi k of EG, sorry, k minus 1 of EG, and so on. But I can stop here. Because one of the wonderful properties of EG is that it's contractible. So this is 0 and this is 0. So what do you know? So pi k of BG is pi k minus 1 of G, and so these are the same. Okay? So our general classification in terms of the classifying space reduces to what we showed explicitly for the case of spheres. Now, the other general formal remark is the following. So I mentioned when I first introduced bundles, you might remember that I spent some time giving some examples of things that were not quite bundles, but almost. Those things were fibrations. And you might remember that I told you about the path fibration. Okay? So let me remind you that if I have X as a topological space, and I choose a point x0 in X, then I can define the Px to be the set of paths, let's call it X of t, in X, such that X at time 0 is x0. Okay? So here's the picture. Here's X, here's a point x0, and I just consider any old path I like. Like this, I'm calling it alpha. Alpha. Now remember that this is a fibration because I can project Px down to X by taking a path alpha and projecting it to alpha at time 1. Well, wherever this path ends up, that's a point in X. And so that's a projection of the infinite dimensional path space down to X. All right? Now, let's observe two things. First of all, the fiber at x0 is the based loops at x0 of X. The set of based loops, right? Because if the endpoint of this path is x0, what's the inverse image? It's all loops that begin and end at x0, and that is, by definition, the loop space at x0. That's remark 1. Remark 2. P of x is contractible. And why is that? So, look, if you have a path, you just pull it back. You can just shrink every path. Okay? I didn't say that we had fixed point, we fixed the endpoint or anything. We can just contract every path. So P of x is contractible. So then, what does that mean? So we have this fibration. Okay, and again, this space is contractible. Just the way we reasoned up there, we can say that pi sub k of omega naught of x at x is pi k plus 1 of x naught. Now notice that when I go from G to BG, the relation here is that this is k minus 1. When I go from x to omega x, the index on the homotopy goes up by 1. So for this reason, B is sometimes called the de-looping functor. So in homotopy theory, B is kind of an inverse to omega. Yeah.
Is the space of base loops a subspace of the path space?
Yes, it is.
But
It's the fiber over x naught.
Well, but shouldn't there be some base loops that aren't contractible?
So you see, this space might be topologically very complicated. But when embedded into this path space, it can be contracted.
Oh,
You see, how am I going to contract this closed loop? Well, I just told you, every loop, I'm just going to pull it along, pull it back. So I'm going to pull this guy back, erasing, literally the way I'm erasing right now, down to the constant loop. Because once I'm in this big path space, nobody says I have to end up at x naught. It's just in that path space, and the path space can end up wherever it likes. Okay. All right. So now let's do another example, which is a lot of fun. So you remember our friend, the Hopf vibration. Let's see what all this says about the Hopf vibration. So we have S1 goes into S3, and then we have the Hopf map projecting down to S2. Okay. So what do we get? Well, we get pi 3 of S1 goes to pi 3 of S2 goes to pi 3 of S3 total space, pi 3 of S2. Then here's our connecting homomorphism, delta, to pi 2. We go down by 1, pi 2 of S2 to pi 2 of S3 goes to pi 2 of, I'm going way too fast. We go from, our connecting homomorphism goes from pi 3 of S2 down to pi 2 of the fiber. This is pi 2 of S3, pi 2 of the base, and down to pi 1 of the fiber, pi 1 of the total space, pi 1 of the base. So I think that's all I need to do. On the other hand, we know a little bit about the homotopy groups of spheres. We just calculated, using our exact sequence, we just calculated the homotopy groups of the circle. So these are 0 all the way up and z here. Okay, so I'm going to do this by erasure. We have 0 here, 0 here, z here. Now we also know the lower homotopy groups of the spheres. So what's pi 3 of S3? Z. And what's pi 2 of S3? 0. We get 0 here. And pi 2 of S2? Z, thank you. And pi 1 of S2, 0. Okay, so at this point of the sequence, we see that there's an isomorphism between Z and Z. Not too surprising. Although if you think through the connecting homomorphism, it's very worthwhile. It's exactly that lassoing operation that I described before. And I encourage you to think about the connecting homomorphism in that case. It's not completely trivial. But the thing I want to stress is this. That guy is trapped between two zeros. So that means, because the sequence is exact, that pi 3 of S2 is Z. That should shock you. It certainly shocked the mathematicians in the 1930s when Hopf first discovered this. After all, if you know a little bit about homology, you know that H3 of S2 is 0. So you see, homology and homotopy are very different beasts. H3 is 0, but pi 3, the higher homotopy group of the two-sphere, is Z. Now, this allows us to define something called the Hopf invariant. You see, here I have a particular map from S3 to S2, the Hopf vibration. It's the one we looked at in great detail a few lectures ago. But now suppose I have any map, or any map, F from S3 to S2. Well, remember that we always have the push-forward map on homotopy groups. So we have F star goes from pi 3 of S3 goes to pi 3 of S2, right? But this, of course, is Z, and this, we have just learned, is Z. Now, what's the most general homomorphism from Z to Z? No. Sorry?
Multiplication.
Multiplication. So the most general homomorphism from Z to Z is determined, if you like, by the image of 1. So 1 generates Z just by adding. And so 1 goes to some integer, and I'll call that integer H of F. That integer is called the Hopf invariant of the map. All right.
Actually, before when you were drawing a picture of this Hopf, then you said that you have these circles which are interlinked.
I'm coming to that. That's exactly where I'm going. Okay. Now, there exists a local formula for H of F. And this is the formula. So let omega represent a two-form on S2, which represents a generator of H2 of S2, which is Z. So, for example, the round, unit volume form, you could choose 1 over 4 pi sine theta d theta wedge d phi. That would be a perfectly good choice for omega. But let me stress that's not the only one. The integral of this on S2 is 1. So that's one way of proving that this generates H2. It's a closed two-form. Cannot be exact. Why can't it be exact? Its integral is non-zero. If it were d of some globally defined form, then by Stokes' theorem, its integral would be 0, but its integral is 1. Good. Okay. All right, but let me stress that omega can be any two-form which represents a generator. So we're free to change this guy by d of a globally well-defined one form. Now, consider the pullback of omega. So the pullback of omega is a closed two-form on S3. But H2 of S3 is 0. So there exists a globally well-defined one form, let's call it theta, on S3, so that d of theta is the pullback of omega. Oh, sorry. That's P star. where P is this projection map. Sorry again. F star, because we're talking about the general Hopton variant. So I want F star here. Okay. I stumbled. Is it clear what I'm doing? So we have this globally well-defined, so we choose an omega, we have a map from S3 to S2, we choose a theta. And now, the formula is h of f is the integral over S3 of theta d theta. Now, in the case that if f equals p is the Hopf vibration, then theta is a called the connection 1 form of our principal fiber bundle. There's a particularly nice one, which we'll write down later in the course, and it is easy to show that f of this p is plus 1. In general, this is an example of a Chern-Simons invariant, which I hope we'll talk about more later on in the course. Now, you might ask me one thing. You might ask, well, what about changing our representative little omega of the volume of the generator of H2? What if I change little omega goes to little omega plus d eta for some globally well-deformed eta on the sphere, right? How does theta change? How does theta change? Well, let's see. So f star of omega goes to f star of omega plus f star of d, but d and f star commute, naturalness. And so that's going to be equal to d of our theta twiddle. But this was equal to d of theta. So theta twiddle is theta plus d of a globally well-defined 1 form. So you could ask me, why is this h of f well-defined? What if I consider the integral of theta twiddle d theta twiddle? Well, I leave this as a little exercise for you to think through. Basically, well, the answer is that it is the same by suitable application of Stokes' theorem. And this is essentially checking the gauge invariance. You see, if you thought of this theta as a gauge field, a gauge 1 form, you would see that this is changing by a gauge transformation. And so this is the same because this is really a gauge invariant quantity.
So you don't have a D. Inner square.
Oh dear. Now I'm in trouble. Okay, let's see what happens. Uh-oh. Okay. Ah. Okay, so let's check it. So it's still true, but the reason is that the change here. Let's see what we get. So we get f star of eta d theta plus theta d of f star of eta plus f star of eta d of f star of eta. Okay? So we need to show that that's equal to 0, right? Now, so what do we do? Well, this is a 2 form, this is a 1 form, so I think I can write this as d of theta f star of eta. I hope so. See, this is a 1 form, this is a 2 form. So this is unfortunately equal to minus d f star eta. Wait, this is already in the right order. This is equal to f star eta and theta minus theta d of f star eta, which is unfortunately okay, sorry. It's a bit more subtle. Okay, okay. All right. Yeah, it was a little trickier than what I thought. So, okay, so from this we get theta df star eta is equal to f star eta d of theta plus d of theta f star eta. But, remember that d of theta is also f star omega, right? So this is f star of eta times omega plus d of theta f star eta. Okay, now eta times omega is a 3 form on the 2 sphere, and so that is 0. Okay. This is a total derivative, so this integrates to 0. And what about this guy, you ask? Well, okay, so this is f star of eta d eta. Now this is a 2 form, some 2 form down on the 2 sphere. So its pullback only involves the coordinates along the 2 sphere. So there's no way it's going to depend on the 3rd coordinate. So it cannot have, even locally, the 3rd coordinate, so it's going to integrate to 0. So this is a pullback of 3 form. 1, 2, 3. Actually, I don't even need that sophisticated argument. This is, again, a 3 form on the 2 sphere. Easier argument. This is equal to 0. Okay. Sorry about that. But now is everybody convinced that this is well defined? Okay. Okay. So it doesn't matter. I really need that property. It doesn't matter which representative of the volume form I take. Okay. Now, about those linking numbers. So, to understand this relation to linking numbers, so let me first say what the claim is. Claim. If A and B, or let's say N1 hat and N2 hat in S2 are regular values of this map, F from S3 to S2, then I claim H of F is equal to the linking number of F inverse of N1 hat and F inverse of N2 hat. Okay? So you see, if I have a map from S3 to S2, and I choose a point in there, and I look at the inverse image, then I'm going to have some one cycle. Okay, there's some one-dimensional thing mapping down to that point. So now what I'm claiming is that if I have 2 points, then I'll have 2 one-dimensional cycles in a 3-sphere, and they have a linking number. I claim that that linking number is this Hopf invariant. Now, to see that relationship, let's back off a little bit and talk about electromagnetism in R3. Okay? So just forget about Hopf for a second, and let's just talk about electromagnetism in R3. So one of Maxwell's equations in a time-independent situation is that del cross B is the current, right? So let's think of this B as a 1 form. Of course, you all know that F mu nu is a 2 form, but in this time-independent situation in 3 dimensions, I can think of B as a 1 form. Let's call it B without a vector, which is B sub I of x dxi. And let's think of our current as a 2 form. So I'm playing some games with Hodge duality here. Epsilon ijk, j sub I dxj, dxk. Now, Maxwell's equation then really reads dB equals j. Says that B is a 1 form, which trivializes the current 2 form. So now consider a closed loop. Let's call it C in R3, which carries some current I. Okay? I. Then our 2 form J looks like, well, J sub k, our vector current, looks like the integral around C of dxk of t, dt, delta 3 of x minus x of t. That's J sub k of x. And I forgot to multiply by capital I. Right, okay, so now let's consider another loop, C prime, okay, and let's consider the integral of B around C prime. So I claim that this is equal to I times the linking number of C with C prime. Now, we can solve for this B, right? That's the Biot-Savart law. So we know that B is equal to minus I over 4 pi, nabla 1 cross the integral around C of dx t over x minus x of t. Okay, so this linking number, L of C prime, is 1 over 4 pi, integral around C1, integral around C2, of x1 minus x2 dot dx1 cross product dx2 divided by x1 minus x2 cubed. All right, so that's a C and a C prime. And now I let you see that I'll skip a few steps here. Why is this the linking number? I should have explained that. Well, by Stokes' theorem, this is equal to the integral of dB around a linking disk, around a spanning disk. Not a linking disk, a spanning disk. So let's fill in the pink curve C prime with this disk D prime. And then using the fact that dB is J, and J is given in terms of this delta function, you see that this is just equal to I times the oriented number of intersections of C, as an orientation, with D prime. Okay? I think it's getting late. Let's straightforward. You can take these formulas, and you can see that L of CC prime is the signed sum of intersections of C with D prime. Okay, so you take the C prime, you span it with a disk, you take the C, and each time it punctures the disk, you get a +1 or a -1, depending on the orientations. Right, the disk has an orientation. We can agree that if C prime is oriented that way, we'll let the normal vector be like that, and then we transport that over the disk. Okay? So we know how to calculate the size.
Excuse me.
Yeah.
So if this disk, if this is a non-trivial knot C prime, how do you make a disk such that the boundary is some?
I think we could still, even if it's a non-trivial knot, we can span it with a disk. Because, and the proof is, that you see a knot in R3 is still an embedding of S1 in R3. And R3 has no non-trivial first homology. So that means there's always a disk that spans that. So even if it's a non-trivial knot, figure 8, trefoil, whatever, you can still find a spanning disk. All right, so you will probably recognize this as the mutual inductance. So this linking number comes up in the mutual inductance of two current-carrying loops. Now, let's suppose that B upper C is the field that we get from a curve C carrying current with I equals 1. And now you can consider the following integral, which should remind you of the Hopf invariant, B upper C, dB upper C. Okay, well, I'm going to skip some steps in the notes, and you're going to end up finding, using the bias of our solution, that this is the linking number of C with itself. Well, that's ill-defined. Right, because B is actually singular on the actual source. Well, that means that to define it, you should take your source and you should displace it a little bit. But now comes a trick. You see, if you displace it, how are you going to displace it? So here's your curve, and here's the normal space. And so now you're going to take some normal vector here, and you're going to push the curve along the normal vector to displace it to another curve, so that you have a well-defined linking number. But of course, this normal vector could twist around, right? There's no natural way in which it points. And so when you displace it, you might end up getting some self-linking. That's why L of CC is ill-defined. Because if you displace it, there's no natural self-linking number. That's called the framing anomaly in knot theory. Okay. Now, back to the Hopf invariant. Okay, so now we have the three sphere here, And let's remove from the three-sphere the north pole. Okay, so on the one hand, we have stereographic projection, I'll call it P north, into R3. And on the other hand, we have the Hopf vibration, and I'll call it PH, down to S2. So now, as I was stressing before, we can choose any representation we like for our generator of the homology, the second homology. So I'm going to take this generator. So here's S2, it's a sphere. And I'm going to take a bump form. Okay? So I'm going to take an omega, which is a smoothed out approximation to a delta function around a point n naught here. Okay? So now think about what the inverse image is. Okay? So first of all, I pull this back and I get some kind of loop up here. And then I push it into R3. And I get some loop. And if I take PH star omega, then P north inverse star of that as my J, let's call that JC. So that's going to be exactly the two form, in this sense, that I associate with a current carrying loop. And as this support shrinks down to a point, this becomes an actual current carrying, this becomes a current carrying loop. Okay, you should be able to believe that. I mean, there's a delta function here, and there's a delta function, essentially a two-dimensional delta function here, concentrated along the loop, right? Yes? Okay. Now, that means that for, okay, if we let B upper C be the corresponding B field, well, that is equal to P north inverse star of this theta, or put more sensibly, Pn star of B upper C is this theta we used in the Hopf invariant. And so now we know that L of CC is 1 when we regularize it in this way. You see this, if I take a smooth little delta bump form here, everything is nice and smooth. There are no delta functions. But I can make it approach the delta function by making the support here approach a point. So I know that if I regularize in this way, then my self-intersection number is 1. And now, let's do the following. So finally, I come to verify the claim. Let's take 2 points, okay? N1 hat and N2 hat. And let's let omega be, say, I don't know, some number lambda, anything you like, plus 1 minus lambda times the two-dimensional delta function of n hat minus n2 hat, d2 n hat. Where lambda is any real number. Okay? So, same story. So here, I get the inverse image. I get some thickened version of a fiber, of a Hopf fiber. And here, I get some thickened version of a Hopf fiber. Okay? And I push that forward, and I get 2 curves, C1 and C2 in R3, which are the images under stereographic projection of the Hopf fibers. Well, what's our magnetic field? Our magnetic field is lambda BC1 plus 1 minus lambda BC2. And so our Hopf invariant, theta d theta, is equal to lambda squared, linking of C1 with C1, plus 2 lambda 1 minus lambda, linking of C1 with C2, plus 1 minus lambda squared, linking of C2 with C2. But the self-linking is 1, so these are both equal to 1. So doing a little algebra, this is 1 minus 2 lambda, 1 minus lambda, plus 2 lambda, 1 minus lambda, linking of C1 with C2. But still, this is independent of the representative. Okay? And for the Hupf map, from S3 to S2, this is equal to 1. There you go. Any two fibers of the Hopf vibration are linked. It's wild. It's completely wild. Okay? But this proves it. And moreover, you see it's essentially coming down to the good old-fashioned Gauss linking number that Gauss defined a long time ago thinking about electricity and magnetism. Something which really fascinated Maxwell. It's got a little later than I expected. So next time I will start by making a few more remarks about the Hopf vibration. In particular, there's a very amusing application of this, which Frank Wilczek and Tony Z observed a long time ago, which is that the Hopf vibration, the O3 nonlinear sigma model in 2+1 dimensions has solitons. You might remember that. Remember, the O3 nonlinear sigma model has a target space which is a two-sphere. If I'm in 2+1 dimensions, solitons are classified by pi2 of the two-sphere. Right? Maps from space, which is R2, into the two-sphere, where the map is a constant at infinity. So there are solitons. Now, what Wilczek and Z did was they said, okay, we have this Hopf map, okay, and we can use this Hopf map to write another term, add a topological term to the nonlinear sigma model, which I'll explain next time. And it has the amusing property that it makes this soliton have a spin which is fractional. You see, in 2+1 dimensions, the spin group is spin 2. Its universal cover is simply connected cover is R, and so you can actually have non-integer spins in 2+1 dimensions. And in fact, that spin is fraction. And these solitons are anyons. If you braid them, the wave function comes up with a funny face. So, okay. So I'll start with that next time, and then we will move on to other applications, both to physics and mathematics, of this long exact sequence that I've explained.